where were we? Did I do a problem on Centroid here? No, I don't think so. I'm going to start from scratch. So we were talking about, we started talking about centroids, okay? Okay? And as I said, there are two types of problem that we will be dealing with. One would be what I call complex areas, and then composite areas. Complex areas, for the lack of a better word, we call them that way, are areas that are basically made or consist of something that is the result of intersection of two or three functions, right? Let's say you have a function, say y1 is f1 of x, and y2, which is f2 of x, and we want to find the centroid of this area. And as I said, what is this? What is centroid? Centroid is analogous to equivalent systems. In other words, if you think about this area being made of these tiny differential areas, and think of each of those as a force, okay? The objective of finding a centroid is to find a location where you can move all these forces, which is a total dA, or total area, but by moving that to that point, there is no moment that you should put there. In other words, from the concept of equivalent systems, what does that mean? That means you find this location in such a way that the moment of all these forces would be zero. And then that will give you this distance, which we call that x bar. In fact, if you look at x bar, okay, is this, is x dA divided by the integral of dA. So you find this because the product of that and the total area, which is a moment, right? If this is a force, this is a distance times force means a moment, right? Is this, is the sum of the product of each of these individual little areas and their moment arm. So you don't have to remember it that way, but at least it's good to know there's this analogy exists. And the y bar is found from a similar relationship. So how do we calculate these? In order to demonstrate that, I would start with an example. But let me in general first say that for x bar, you always consider a differential area whose sides are parallel to the y-axis. In other words, you identify of all these a general differential area which is located at the general position x, meaning that at any point here, right? And the width of this is obviously a dx. The height would be what? Height is the value that you derive from evaluating this function at that point x, and then this one, which is y1, at that point x, you subtract these two, okay? y2 minus y1 times dx, right? That will give you that differential area, okay? So that's what you do for finding x bar. For y bar, you consider, so this is for x bar. for y bar, you consider a differential area whose sides are parallel to x-axis. In other words, this dA varies from here, the lower bound, to the upper bound, okay? So the thickness of this is dy, and the value here, as this thing is moving from here to the top, this distance is the x that you get from that function, and this is the x value that you find for that y value from this function. Or in other words, this is x1. So dA in this case, okay, would be x1 minus x2 times dy. So in other words, this is a function of x, because it is f2 of x minus f1 of x. Here, this should be a function of y. So from the first integral of a function, you find x in terms of y, same thing with the second one, put it there, and you have dA in that case. So let's demonstrate this and show in a step-by-step what is an easy way of calculating these. I'm sure you've had this in calculus, so it's a repetition basically here. The only difference is that I would present in a methodical, organized way that I hope would be easier for you to perform those integration and find these the centroids for this case. And as I said, it's not, and this is a very easy concept, and no matter what kind of function I give you, it all comes down to evaluation of these integrals. So let's at least set up the general procedure, okay? So I'm going to start with an example, and this is the example. Let's say you have an area, okay, described or given by the intersection of two functions. This function, I call that y2, is mx. This one, y1, is kx squared. So you want to find the centroid of this area, and which is basically the area that is trapped between these two curves, where they intersect at this point where this is A and this is H, okay? So this is how we proceed. So these are the steps that we follow. First, let's start with x bar. Step one, you need to define dA. I said dA is described by a differential element whose sides are parallel to y-axis, okay? So this is dx at a general point x. So the area of this rectangle would be this y1, which is given by this function, minus y2 given by that function. So this would be then y2 minus y1 times dx. But what is y2? y2 is mx, y1 is kx squared times dx. We do have, or we can find the value of those parameters, by the way, m and x, right? Because this point coordinates are given, so just substitute that in the two functions to find those. For instance, from here, okay, for x equal to a and y is equal to h, you will get what? You have h is equal to m times a, therefore m is h over a, right? If you substitute that point into this function, you get h is equal to k a squared, or k is h over a squared. So we have those values. I'll put them in here so we can find them in terms of the given values of these two, that point. So if I do that, I get dA is equal to h over a x minus h over a squared, okay, x squared dx, or I would simplify that h over a times x minus x squared over a dx. So that's step number one. I fully described dA. Step number two, okay, you just simply evaluate the integral of dA. dA goes from here all the way to here, sweeps the entire area, which means from 0 to a. So you just substitute these values, h over a times x minus x squared over a dx, the integral from 0 to a, just perform the integration, h over a comes out of the integral, so you have the integral from 0 to a of x minus x squared over a dx, or that 0 to a dA becomes h over a. Perform this integration, you have basically x squared over 2 minus x cubed over 3a, okay, evaluated from 0 to a. So you substitute that, you have h over a, right, times a squared over 2, right, minus a squared over 3. This cancels out with that. You have h a over 6. So that's the integral of dA. So that's the second step. The third step, now you just perform finding the numerator. You already have the denominator, you find the numerator. Numerator is easy, right? So step number 3, find x times dA. You already have dA, a function for dA, or this is a simplified version. You just have to multiply that by x. And bounds of integrations are the same, 0 to a. So that would be h over a, integral from 0 to a of x times this, okay? So you have basically x squared, okay, minus x cubed over a dx, okay? So if you do that, you get then, gives you h over a of the integral x cubed over 3 minus x 4 over 4a, 0 to a. So you have h over a of a cubed over 3 minus a cubed over 4. So if you simplify this, this a with one of these cancels out, so you get h a squared over 12. Okay? So all you need to do is just divide that with the integral of dA to find x bar. So x bar is what? Is the integral of x dA, which is this, divided by the integral of dA. So is h a over 12 divided by this one, h a over 6. So it would be simply a over 2. Okay? So that's x bar, which means, what it means is that wherever this centroid is located right along a line that is halfway here. Okay? Now you need to find y bar. The good news is, to evaluate y bar, you see that you have already calculated the total area. That's what it is, right? So you don't have to redo that. So for y bar, you only have to find out this integral. Of course, for doing that integral, you need to redefine dA for this case. And in this case, of course, so let me actually underline here so that these steps are clear where we are. So for y bar, we just need to evaluate dA for the purpose of setting up that integral. And in this case now, as I said, for this case, dA should be considered with its size parallel to the x-axis. So, in other words, this is dy, okay? This was y2, okay, which is h over ax. This is y1, which was given as h over a squared, x squared. But what are these? In other words, what is this distance? This is, if I call that x1, is the x that is evaluated from this function, right? And this is x2, means the value of x at that point, which is evaluated from this function. So dA then, in this case, if I just write it down, would be x1 minus x2 times dy, the area of this rectangle. So I need to set x1. x1 is from here. In other words, you need to find x as a function of y. So if you do that from here, for x1, you do what? You have y, a squared over h, right, is equal to x squared, or x is what? Is a y half over the square root of h. So that is x1. For x2, you just simply need to evaluate it from here. So if you write that function, right, y is h over ax, or x is a y divided by h. So I would just call this x1, this is x2. So dA then would be what? Just what? X1 minus x2. I will factor a out to make it a little bit easier. So you have a y to the power of half divided by square root of h minus y divided by h dy. This is dA for evaluating this integral, which is y dA. And so what we need to do here is, all I need is to evaluate y dA, dA being this. So let's do that. But what dA now varies from here all the way to here. That is from 0 all the way to h. So that's the bound of integral. So I have 0 to h of y times this. So I take a out, y times that will give me y 3/2 divided by the square root of h minus y times that would be y squared divided by h, right, times dy. Okay? So perform the integration, you have a, right, times 2/5 of y to the 5/2 minus 1/5 1/3 of y cubed over h from 0 to h. So substitute for h, you get a times, that would become 5 halves, okay? So it would be, okay, y to the 5, I'm sorry, h to the 5 half. And this is h to the 1 half, so that would be 2/5 of h2, because it would be h4 divided by 2. So it would be h squared minus, same thing here, 1/3 of h squared. Okay? So that'll give me a h squared over 15. That's, if I didn't make a mistake, that's, sounds like it, right? So this is what? This is this integral. In order to find y bar, you just need to divide that by the total area, which you had already from step 1 evaluated, and that was what? We have that here, right? This was the integral of dA, right? Which we have found. So this is dA, integral of dA, or the total area. This is that integral. Divide the two, and I should have left more space, especially that you're taking the video. I hope that would be clear. So y bar, let me do it in this color, y bar would be a h squared over 15 divided by h a over 6. So this would be 2, this would be 5, this and this cancel out, this and that cancel out. So y bar turns out to be 2/5 of h. Okay? So what that means is what? The centroid of this area is located at a point which is halfway of the distance here, and this, which is y bar, is 2/5 of h. That's where the centroid is. Okay? Easy, right? The only thing in this case that you really need to know, forget about all these steps of integration. Obviously, no matter what the area is, you have all these integration stuff, right? You remember the first step is for x bar, you identify a differential area whose sides are parallel to the y-axis. So that would be a function of x. So you evaluate that, and then take the integral of that as a second step, right? So you will find the numerator of in this expression. I'm sorry, the denominator. Now, in order to find the numerator, you just, whatever function you had here, multiply that by x, which is what we did, and then evaluate that, divide that with this, that will give you x bar. For y bar, the only thing is you just need to set up the differential area with sides parallel to the x-axis, so it will be a function of y. dA will be a function of y. So the bound of integration are for variation of y, in this case was from 0 to h. Evaluate that, divide it by the same integral. You've already evaluated it in the first place, and then you got y bar. Okay? So that's it. Any questions? No? Yes?
So at the beginning where you set h bar equal to like all that, is that like a given?
Which one?
Um,
These?
Yeah.
Yeah, these are the expressions that you use to find x bar and y bar.
Okay.
Yes, these are, yeah, this is different, yes.
Yeah, how do you choose x1 and x2, like how do you differentiate? It just have to be like?
Well,
all
good
possible?
question. Let me actually, maybe it's got a little bit messy here, so let me go over that a step, because that's important, right? So let me just, for not, at least, nothing else but like a summary, let me show you, okay? So what you have here, you have two functions in general, right? So regardless of the shape, I call this y2, which is a function of x, right? Then you have y1, which is also a function of x. Doesn't matter what order it is, okay? So for x bar, you need to consider a differential element like this, right? So area of this, in other words, you need to define a dA like this, right? So what is the area of this dA? Is this minus this, right, times dx. But what are these two? These are the values of these two functions evaluated at point x. So in other words, this is y1 for which you substitute x. So basically this would be f of x, right? Whatever that is, or f1 of x. This one, or actually this would be, this is y2 minus 1. So it would be f2x minus, right, find 2x minus y1. So this is y2 minus this. So minus f1 of x. So for dx probably was easy because the way these functions are given as y is equal to something which is a function of x. But for dA, for the case of y bar, you consider a differential element that is like this. This is now for your y bar, this is your differential element, right? So what is this? This is the x value, because you're considering a general, basically, distance y, right? And this is dy. So at any point y, you want to find the x value corresponding to that y on this function, and for that y, you find the corresponding value for that, right? In other words, if this is x1, I call this x2. Difference of the two times dy is the dA, right? So in this function, you need to find x as a function of y. The y is given. In this case, x was given. In this case, y is given. So you need to find, in other words, y is your variable. In this case, x was the variable. So you need to find x as a function of that variable y. So from whatever this function is, here you need to find x, which would be basically the inverse function of y, right? Same thing there. And if the difference of the two times dy. Okay. But most of the problems you end up with is parabolic or linear. Even if it is, you know, higher order polynomial, it is usually the way that you can figure it out. But to be honest, I'm glad you asked that question. As you can see, it's obvious that in most engineering applications, unless you have some very complicated design of a shape or whatever, you don't come across shapes that are given by some functions like this, right? Unless you're working as a civil engineer for an architect, and the architects like all these very interesting shapes to design buildings or whatnot. Mechanical engineers or, you know, so on. What kind of shapes do you come across? Maybe a piece of sheet metal, you cut it for some whatever applications, or things that are mainly made of what we call composite shapes, which is the second case that we're dealing with. So composite shapes or areas consist of simple geometric shapes that are put together. Let me start actually with a specific example because it's easier to demonstrate the concept through a specific example. So I'm gonna use this as an example. Let's say you have a shape like this that is given to you and you want to find its centroid. So you have something like this. You have a piece of, let's say, sheet metal, a circle is cut out of here, so you have a shape like this, and for whatever applications, you want to find the centroid of that. All the dimensions are given. For instance, this is given as 60 millimeter. This distance is given as 80 millimeter. This distance is given as 120 millimeters. A radius of this half circle is 60 millimeter, and radius of this is 40 millimeter. So you want to find the centroid of this shape. So let me sort of formulate or establish, very similar to the previous case, a step-by-step approach. First of all, the integral equations in this case become summation equations. In other words, x bar becomes ai times xi divided by sum of ai, and I will explain what those are. And y bar becomes ai, yi, ai. What ai's are as follows, okay? You would subdivide this shape into simple geometric shapes. What I mean by simple geometric shapes, things like a rectangle, a triangle, a circle, half a circle, quarter of a circle. In your book, for all those simple shapes, you're given a table that tabulates the centroid of each of those shapes. What do I mean by that? For instance, if you have a right angle triangle, right, you would know that the centroid of this shape is located, if this is, say, A, this is H, is located at 1/3 of the distance from this side and 1/3 of the distance from here. For a quarter of a circle, centroid being here, is 4r over 3 pi from here and 4r over 3 pi from here. All these are tabulated in that table that you have. You don't have to memorize them. You're given that table. So AIs refer to shapes that you create that would be basically one of these shapes, half a circle, whatnot. So that's what we do. As a step number one, divide into simple shapes. I mean simple geometric shapes. This is what I would do. For instance, I will consider this triangle as A1. I would say this rectangle, okay, is A2. And if I have a solid shape that some piece is cut out of that, which is another simple shape, I would consider that to be a negative area. So from this rectangle, I mean, this rectangle doesn't exist because this piece has been cut out. I call this A3, and as you see later, to differentiate that with the other values, I put a bracket on this two sides, meaning this has a negative value. In all operations, I consider that as a negative value. Then I will consider, say, this area, this half a circle as A4, and from that area, again, this little half a circle has been cut out. I consider that as A5, and it is going to be negative. There are other ways. I mean, this is not the only way you can divide this area, any which way you want, as long as those sub-areas are simple geometric shapes. For instance, I could have just considered this and this as two areas, and a full circle has been cut out of them both. That's fine too. That's the way I do it. So that's the step one. The step two, now things get easier. All you do, start with a table. This is how you set up this table. First column, you just list those areas that you have created. Okay? So this is step two. So I have A1, A2, and in order to keep track of those negative values, when I write A3, I put this bracket to be careful that is a negative area. A4 and A5, which is also negative. The next column, I would simply list those AI values for each of those sub-areas in whatever units that I have here. For instance, this is a triangle, so it would be 60 times 120 divided by 2, so it would be 3,600 millimeters squared. For this rectangle, 80 times 120, so it would be 9,600 millimeters squared. For this half a circle is pi r, which is 40 squared divided by 2, but that is negative. For that half circle, you have pi times its radius, 60 squared divided by 2, okay? And for this one is the same as that one, so I have pi 40 squared divided by 2 negative. As I said, these AIs are the areas of each of these pieces. So, and I'm gonna just finish this and stop here, do it the next time, finish it the next time. But you look, if you add these up, what do you get? The denominator of these two formulas. In other words, this is sigma AI. Now, as you will see, now as the next one, well, I would find xi for each of these, then I create another column, xi AI, as I will show you, in such a way that when I finish this, I add these up, I end up, for instance, with the numerator of the first one. So dividing these two will give me the x bar. But let me stop here. We'll go through this more thoroughly, and next time we'll finish it.